In this module, we will look at synchronous machines in very large sizes, and some of them are controlled by thyristor-based converters, as we'll see. They are called load-commutated inverter supplied synchronous motor drives. And we'll also look at synchronous generators, which are used, for example, in power plants. So let's start with this LCI drives. And so what's going on here is that we have synchronous machine where on the rotor we have, instead of permanent magnets perhaps because they are in such large sizes, we have a winding which through whatever means is supplied a DC current. So that's the field current I sub F that is being supplied to the rotor windings, producing north and south poles. And then on the stator, we have three-phase windings, and these three-phase windings are supplied appropriate currents, but through a thyristor-based converter arrangement, as shown here. So in this, the input is coming from the utility, and it's being converted to a DC current over here, which can be adjusted in magnitude. But unlike the previous schemes where we had a voltage here across a capacitor, here we have an inductor in series, and we are controlling the current through this inductor. And this current is then being supplied to the three-phase winding through this load-commutated inverter. So the commutation of this inverter takes place, the current commutation in this inverter takes place because of the back EMFs that are generated within the synchronous machine. And our purpose is really not to go into that kind of detail here, just to indicate that there is a class of machines like this over here. So we'll leave it at that, and we'll go into synchronous generators, which are used in power plants in very large ratings, 100 megawatts, perhaps 500 megawatts, very large, and they're directly connected to the utility without any power processing unit, no power electronics, and they have three-phase windings on the stator and the DC field winding on the rotor, which is supplied by a DC current, and we will not go into details as to how that DC current is derived. It could be through slip rings and brushes, but that is not usually the case. We use so-called static exciter. But again, that's beyond the scope of this course, so we will not go into it. But we'll see here that in these synchronous generators, by controlling the rotor field winding, we can then control the reactive power that is either supplied by this generator or drawn by this generator. So that's a very advantageous feature. And that we see in this diagram here in terms of this per phase equivalent circuit. We have this back EMF that is generated within this generator here. We have the synchronous reactance. And please note the direction of the current. It's coming out of the generator. So it's defined in a generator mode, if you will, is coming out of the generator, and it's going into the utility system, which is represented on a per phase basis by this voltage source here. And resistances are very small, so for making it simpler explanation here, those are neglected over here. So you can see that in a system like this, where you have two AC sources connected through this inductance, reactance X sub S, the power flow on a three-phase basis can be written by this equation over here. And the power always flows from the leading voltage to the other. So if delta in this diagram or this expression is positive, then the power is flowing from the machine to the utility. That is, the machine is acting as a generator. And if delta were to become negative, then it will be the other way around. That is, this machine is operating as a motor. So that is what's shown in this diagram here, where as a function of delta, when this delta is positive, this machine is operating as a generator, otherwise is operating as a motor here. So in this case, unlike so-called PMAC machines, brushless DC machines, delta is not kept at 90 degrees. In these machines, there is no power electronics. These generators are directly connected to the utility grid through some transformers. So this delta can change or will change depending upon the amount of power that needs to be supplied. But at a given power level, again, it's in the generator mode, we can control the reactive power. So let's take this first case here. It's the unity power factor of operation, where the current phasor is as shown over here in the direction of V sub A, and we have certain back EMF, and its magnitude is indicated by the length of this phasor. But what if we want to supply reactive power to the grid from this generator? What we will do is we will make this field current greater than what it was in the unity power factor case. So you can see here that now this back EMF has a larger amplitude. And in this case, the current would be, current phasor would be in this, at this angle, and you can see the projection of this current phasor onto the V sub A axis. That is the same, that corresponds to real power, is the same as this in this diagram over here, in the unity power factor case. So you can see that we are supplying the same power, but this machine, since I sub A is in the direction shown, which is not in phase with V sub A, is supplying reactive power. And usually, when you see current lagging the voltage, we think of reactive power being drawn. But that's not the case here. The reason is that current IA was defined as coming out of the generator. So that is the reason why the reactive power is in fact being supplied to the grid in this diagram over here, where we have the field current greater than the current in the unity power factor case, which then results in a larger amplitude for the back EMF. The opposite is true if we want to draw reactive power. In that case, we will make the field current smaller than that in the unity power factor case. This EFA here is smaller than the unity power factor case, and you can see that IA is in this case leading the voltage and being defined as it is, its direction. This is actually drawing reactive power from the utility grid. Although the real power in all these three cases is the same, and since the current here is smaller, the field current is called under excitation. Since the field current here is larger, it's called over excitation. So this is a very helpful feature of synchronous generators, actually really the backbone of supplying reactive power in power systems. That is, by controlling the field current in these generators, we can control the real and reactive power we can control the reactive power that these generators either draw or supply. So that brings us to the summary of this module, where we have seen this LCI supplied synchronous motor drives, and we have seen the synchronous generators and how we can adjust the reactive power for a given power level to be either positive or negative.